Good day to everyone. I'm Ian Panganiban and I'll be presenting about From Field to the Cloud, a geoperson's Python toolchain. So a little bit about myself. So I'm the head of cloud and infrastructure of Irai Energy. So basically we're dealing with unstructured data in the geoscience space. So in my previous work, in my previous life, as I say, I've worked with surveying, geomatics engineering, which deals with a lot of field works and, of course, going into the field and working on and gathering data and making it some insights. And I'm also part of the Phosphor GPH, so basically we're dealing with open source and advocating and promoting the use of open source software for geospatial applications. So here's my Twitter and GitHub handle. So if you want to contact with me and message me, you're free to do so. So here's the agenda of this presentation. So I start with some introduction, and I'll go with the geodata, a little bit about spatial 101, about our workflows, and some use cases and the takeaway for this. So just an introduction. So as you can see on the left-hand side, so this is basically the location of all the oil wells throughout that was drilled in Australia. And most of these are already dried up, so they were doing some exploration and they're extracting oils from it. Oil or exploring oil or gas. So here's the abstract of this presentation that I have sent to for this conference. So uh, So basically, the topic of this presentation is that a lot of geospatial applications are now being penetrated or penetrating throughout the different industries. So from energy and healthcare to disaster reduction. So Python plays a vital role because a lot of these domain experts are now working and trying to make sense out of their data and building their analysis, such that they need to have a good or a simple language or a simple programming language that will allow them to extract those information. So for this talk or for this presentation, I'll be working or showing you some workflow and as well as some tools that we constantly use for in the geospatial sense or the geospatial space. So this is an example in the geospatial application or geospatial um, application in the disaster risk reduction. So this is a 3D hazard map. So this is from the Philippines. So we have this. Basically, we assess the different hazards, or they've assessed the different hazards that will come across in a particular place. So, for example, this is a hazard map. So, flood hazard map. So, as you can see, it has a medium hazard setup, but as you can see, since this is a flat terrain, it has a little to none landslide susceptibility, and but it has a high storm surge because it is near the ocean or near a body of water that will induce or introduce some flooding. So another example or another use case is the domain of energy. So on the left hand side, you can see that there is what we call a tidal current model. So there is now a shift in the renewable, not necessarily a shift, but an addition to renewable energy, wherein we all know that there's solar, wind, hydropower, geothermal, biomass, and so on. But there is now a new or an additional renewable resource, is what they call ocean renewable energy, in which I can proudly say I was a part of it before, wherein we it's trying to extract or gather energy from ocean energy or from ocean powered resource or energy resource. So as I've mentioned, on the right hand side is the location of the wells. So another example or another real world use case is that it's in the domain of asset management. So if you're into, let's say, construction, or let's say you're managing different assets of your company or organization, most likely you need to put it in a geospatial, or you need to geolocate your assets. So on the left hand side, so this is a common use case wherein you're monitoring your forest or the trees you planted for that organization, because there's a lot of um, organizations now wherein they are doing this carbon neutral and corporate social responsibility exercise wherein they're planting trees, for example. So on the right hand side is mostly on the construction projects inside the Philippines. So it's more of a distribution projects. So you can have various ways of how you want to use your geospatial data or location data for the benefit of your projects. So when we talk about geo, there's a lot of things about geo. So what I've shown earlier is only part of the geospatial context. There's a lot, actually. There's a lot more geo that happens that we tend to forget, that we try to encapsulate all of the industries, or we just know, okay, geo is just getting from point A to point B. But there's a lot more sectors or components or segments about it. So we have what we call the geospatial, which is that I'll be talking mostly about today. There's also geomechanics, geophysics, geochemistry. You also have geology, petrophysics, geography, and of course, amongst others. So as you can see here, there's various geo-related topics, but they all focus on the study of the Earth. And for us to understand or the study of the Earth, you need to have a lot of domain expertise and so on, and expertise and knowledge for it. And when we talk about geospatial, we're just talking about the technology or the study above the surface of the Earth, or just near surface of the Earth. So anything on the surface until above. Everything around this other parts here, are except for geography, of course, they now deal with the internals or the subsurface domain. So when we talk about geo data, okay, now we're focusing on the geospatial data. In this case, is that we try to model the world into different data layers. So this is in the GIS world, wherein you have different data slices, wherein it can come from, let's say, you have, let's say, elevation, transportation, addresses, boundaries, water features. Basically, is what we can see in the real world, we are creating different layers. It's like your pizza. You have your base, you have your crust, then you have your sauce, then you have your cheese, then you have your pepperoni, then if you like pineapple, you can put it on top as well. So when we talk about geodata, we're talking about these different layers across this stack. So before I go into the specifics of geodata, let's talk about data in general. Because geodata, if you're into the data science domain, we all know that you have what we call the three types of data. In this case, you have structured data, unstructured, and semi-structured data. Geodata belongs or has different, or they fill up all of these slices here, or this graphs here, because when we talk about unstructured data, we talk about documents, we talk about files, PowerPoints, present images, and so on. So geodata, they can come from those sources as well. So if you're familiar with land titles, for example, they are not actually structured. In the Philippines, we have what we call our land titles are actually written in the previous years. It was written in Spanish, then you need to translate it. And some old titles are like that. So that's why they come from the unstructured. Because those land titles contain your bounds of your, let's say, house. and the location of your house. And most of the time, once we translate that unstructured data into structured formats now, we now contain into a database. So most of the time now, the use of geodata is now focused on the structured sense. We are not anymore working with the unstructured and semi-structured. So that's why when we proceed or when we're going to work or show the different applications of geodata, mostly they are now coming from the structured domain or structured component, not anymore in the structure. So it's now easier to work with. So when we talk about geodata or geospatial data, we are talking about two different types of data here. We have what we call the vector data and of course raster data. So when we think about vector data, it's basically more focused on the modeling of discrete features with precise shapes and boundaries. So for example, let's model a building. The building has, let's say, four corners. So in the vector representation, it consists of 4 points, and you connect them into one polygon or let's say box. But once you now go into a translate it into raster data, so raster data, it's basically focused on modeling continuous phenomena and images of the Earth. So from here, we are now talking about pixels. So instead of just points now, we're now talking about pixels. So in the using the same example of a building, which consists of let's say 4 points, if you translate it into a raster data or an image, it can now become, let's say, 1 pixel or you can have 4 pixels to represent your building. So I'll show some examples for the next few slides. So as mentioned, vector data consists of points, lines, and polygons. So in the left-hand side, you have the OpenStreetMap. So OpenStreetMap is it's like your Google Maps, but it's free and you can pull down the data, and mostly it's more complete actually versus Google Maps, if I'm going to say. And you can actually extract the nodes, the lines, the polygons of this OpenStreetMap. So when you download, let's say, an OpenStreetMap data, you'll have this different points, lines, and polygons. But there are other structures of vector data as well. It's not just limited to, let's say, mapping. It's also representing, or it also cascades into the petrophysics log data. So think of it as your signal processing if you're into the signal processing space. But just an FYI, petrophysics log data belongs to the oil and gas space, wherein when they usually drill or do an exploration, they get these different signals. If and some of these patterns here would indicate if there is oil or if there are risks inside that when they're drilling. And from that's for the petrophysics. And now we are into this space of, let's say, building 3D point clouds. If you're familiar with, let's say, self-driving cars, they are now attaching LiDAR sensors, or let's say, I think the iPhone or the iPad contains some LiDAR to produce, let's say, those augmented reality. So these 3D point clouds, they are being generated by shooting a lot of lasers, then trying to model and create those points into a space. So most of these are the vector types of data wherein you can distinctly identify up to the point level. For raster data, it's now a little bit different because, as mentioned, raster data contains about pixels in this case. So for satellite images, for example, so these are the different examples. You got satellite images, thin sections, and drone images. So for satellite images, so if you're into, let's say the military or war type films wherein they have this big map, or they're doing some, let's say, some zooming in to a certain place, they all use satellite images. So essentially, a satellite will just take a picture, but do note that why it belongs to raster data or geodata, geospatial data, because for every pixel that lies in this image contains a position. It contains some value or a part of the location. And these are also similar to drone images. So if you're going to fly a drone, then you're going to take a picture. As long as the drone, or you can geo-reference this image to to a location on the ground, you can also point that. But there's also what we call a type of raster data that doesn't only produce location, but it is also part of the geo data. Since thin sections, they are coming from the subsurface domain. This is similar to the petrophysics lab data, wherein some of these images contain some minerals that will translate if there is oil or belong to a geological point of view. So that's why when we talk about geodata, we should look at it on the more generic sense, that it should not only focus on the geospatial, but also to assess the other aspects of that geospace. So yeah, and one thing that we need to talk about before I go into the geospatial or when we start working or coding, right, is that the resolution of our data. Because geodata containing or geospatial data, once you have what we call this resolution. So resolution means that it is the measure of object, smallest object that can be resolved by a sensor. So this is true whether it's spatial data or let's say the previous one there or the sensor that we're using for getting those thin sections. So as you can see in this image here, you can see that a 1 meter resolution actually provides more level of detail against 10 meters, 30 meters, and let's say 250 meters. This just means that for every pixel for this image, it contains 1 meter of resolution. And for this one pixel here, it contains 250 meters. As you can see, there's not any more distinction between 250 meters worth of if you're going into that resolution. So something to note here is that the type or the resolution determines the type of application that you can build. It's, for example, if you're going to use a 250-meter resolution worth of data, can you use that for, let's say, determining traffic? Right? You cannot simply do that because you're not going to, because our roads are actually, let's say, 1 meter up to, let's say, 1 meter to 5 meters worth of resolution. Maybe you need up to letter number one, for example. You need to have letter a 1 meter resolution. So another thing to consider is that we also looking at coordinate systems. Is that when we're dealing with geospatial data, is that there's a lot of data out there, and especially on the old data, when you're consolidating different data sets, is that you have this what we call coordinate reference systems. Is that one point of that data or one point can have a different representation into the earth because most of the position or location that we currently have, they are modeled to a specific reference system. So when you're now dealing with consolidating different data sets, you must take to account these coordinate reference systems because you need to have, when you're going to process data, you need to have this coordinate reference systems to be in a similar space. So now we're going to move on to the workflow and tools. So this is mostly focused on the processing and of course the libraries that we're going to use. So I've done the Geospatial 101 already, which is focused on geodata. So in the traditional sense, when we talk about geospatial processing or geo workflow, is that you have, let's say, a GIS system, you apply some level of methodology, and you now consider yourself a geoscientist or a geospatial engineer. But now there's actually a shift because the problem with having a desktop GIS system is that, or this GIS systems provided here, is that you need to be well versed on how to implement your data, or you need to be a geomatics engineer to know what GIS means. Now, we are now moving into the different domain wherein we're now pushing into this cross domain workflow. Wherein from this cross domain workflow, for example, if you're a biologist doing some um, bird migratory monitoring, you may now work into you're not only focused on the GIS, you're also looking at other data sets. So this is now where the glue, which is which is Python, comes into spectrum. And this is also enables the different cloud providers, because a lot of this big three cloud providers now actually have support for processing geospatial data. So for example, if you're in Azure, you have what we call the Azure Maps, wherein you have some level of geo processing. For Google Cloud Platform, I think there's the what we call the Google Earth Engine, which has the most sophisticated way of processing geospatial data. So all of these tools or workflow, you can now combine them into to a or combine it with a workflow, and you can now call yourself even a geoscientist. But something that we need to consider is that the geo workflow should be guided by the domain expert that you're running into or working with, because as I've mentioned, all of the considerations in using the geodata, using resolution, coordinate reference system, they should be taken into account when you're processing and working on these types of data. So we're going to go through this workflow together. Okay, so let's start with getting the data. So when you're getting data, you can have various formats, or when various forms of it. You can do field surveying, drones, or using mobile GPS. Or you can also do it via gathering online sources. So, for example, you have USGS, Copernicus, Open Aerial Map, Open Topography, OpenStreetMap. As I mentioned, you can download the nodes, or Sentinel Hub. Majority of these, they provide a repository of raster data, except, let's say, for OpenStreetMap, which provides you the vectors or the nodes on the ground. So when we talk about the data that is being presented here, is that this is a, a vector data which contains of the road network. So the red ones or the pink ones here highlights the road networks. Then you have the list of establishments in the yellow, and of course the points of interest, which are in the middle of those establishments, or these polygons. And you also have the raster data, which is below the vector data, which is basically a Landsat or a satellite image that supports the entire context. So now we're now dealing into the Python domain, wherein we're now working with reading and writing data. So essentially, if we're going to look at it, there's nothing different about special about geo data or geospatial data, as long as you know the workflow or you know the model that you're trying to do or implement. So in this case, we are going to, most of the time, I'm using what we call GeoPandas to read vector data, because it has already those connectors and those APIs available to pull and read different types of spatial or vector data in this case. So if you want to connect directly to OpenStreetMap, because if you want to download OpenStreetMap data, you need to go into you can use their API. There's the Overpass Turbo API, where you can pull the data given a certain boundary, and you pull the data. But in Python, there's already a good library to it, which is the OSMNX. So it's basically it abstracts the Overpass Turbo API to pull the data out of OpenStreetMap. And for raster data, this is already a very good convention, which is what we call rasterio or raster IO, which reads and writes geospatial raster data. And most of you have used Pillow, Scikit image to read images, but if you use those, for example, if you use Pillow or Scikit image to read a geospatial raster data, you'll not be able to retrieve the coordinate reference systems, the bounding boxes, other things that are more important that makes that raster data geo. So this is just an example of a of when you're going to read using GeoPandas. So basically, you have, let's say, this GIS shapefile. You read it. You can see if you read that file, you're going to have this different boundaries or different columns that presents the attributes of this shapefile or this vector data. And notice you have an additional column which defines the geometry of that data. So this what makes geodata special. So in this case, we have the geometry column available because it defines the boundaries for it. So for raster data, this is also similar if you're going to use rasterio. So this is a TIFF image. When you process it, you read it, you just run open. As you can see here, this is what I'm saying about spatial context. If you're going to use Pillow, you can only get the, let's say, width and height, but you're not able to get the bands or the indexes for it. So for example, because this stiff image, it has 3 layers. So it's the RGB. You can have more, you can have 7 or 8. So for example, for satellite images, Landsat, I believe it's about 10 or 11 bands or 11 layers of image that are stacked together. So essentially, you can think of it as that if you're looking at it in a time scale, you can have, let's say, in a temporal scale and you're stacking them together. So in the geospatial sense or satellite imagery sense or remote sensing sense, is that you have this bands which are stacked together. So for example, if we're going to read this Landsat image, we have, because I've read band 1, so you're going to produce, let's say, a NumPy array. So essentially, that's the essential geospatial toolchain. Those are the two things that you need to do to read geospatial data. Then, for the processing, once you have read geospatial data, all of the libraries of Python is now available for your use case. So from pandas, let's say NumPy, Bokeh, Matplot, pandas, scikit image, network X, you can now use those things in the general sense. So that's why if you're going to look at it, the geospatial toolchain is only two. You need to read and write the data. That's it. Now the context of processing it, it's now up to you because you can tie up once you read through geospatial data, you can tie it up with your own API, you can tie it up with your own processing systems and so on. But something that we should take note is we need to pre-process the data because of, I've mentioned earlier, you have the resolution problem and of course you have the coordinate reference system. So this is a good meme actually. Which one is correct here? Is latitude X or latitude Y? The correct answer here is actually latitude Y because latitude, when we talk about when we say we always say position is always latitude longitude, but in the Cartesian plane, right, it's always x and y, so it's the reverse. Longitude is the x, it moves x. But pre-processing, why it matters is that, as I've mentioned, since you have a lot of coordinate reference systems, you need to have consistency amongst uh, those different data sets. So if you want to have, let's say, meters, you need to work all throughout in meters. If you're working through degrees, minutes, seconds, you need to work through all of it, degrees, minutes, seconds. It just promotes consistency amongst the data. So here's just an example of it. So it's a pre-processing using coordinate transform. As you can see here, we're using 4326. So if you're using GeoPandas, so the data frame, once we read through it, you can actually implement a coordinate transform immediately. So EPSG is the European Petroleum Society and of Geosciences, I believe. So you have that, wherein they basically list of all. So as you can see here, there's already a difference in the units of that location. So from degrees, you are now doing it into a meter, and you can also see in the geometry column, it's now different. So from 121, it's now becoming like this 1347 because one layer or one component is that it belongs to decimeters. So similarly, from raster, it's also we can also do a similar exercise. If you're given, let's say, from meters, you can transform it as well. But it's more of a hacky way to do it. It's not a clean API because the problem with the rasters is that you can also create other formats because you're working with in a numpy array instead of a data frame as you seen earlier because you're now doing this numpy. But it's also quite simple, and there's only what we call the reproject column. As long as you have that, then you provide the transformation parameters of it. Then, yeah, basically you define the transformation parameters. Then you have, let's say, the target of the transformation parameter. Then you can now couple or build or reproject it. So when we're talking about processing, so as I've said here, processing spatial data is simple when you have identified the application and the type of workflow. So it's very simple. You have raster data and vector data, and they all have vector or raster operations. So since you're now having what we call a numpy array, you can now work with, let's say, the matrix operations, let's say plus, minus, divide, and multiply, those matrix ops. Then you can also implement masking, image filters, for example, denoising, and so on. So you can also do convert to vector. For vector data, it's quite different because you're dealing with points times polygons. You can only do union, dissolve, intersection. You can also do, let's say, the nearest neighbor. So for example, because it's points. You can also implement nearest neighbor and raster operations, but it's mostly on the pixel level. You're just dealing with pixels. But if you're into vector operations, so ideally, if you're doing nearest neighbor, ideally you're going to use, let's say, the vector ops because it's more detailed. But sometimes, if you don't have that granularity available, you can also use raster operations. So now we go into the visualization part, wherein it's again it's very simple. Actually, it's very simple to do it. You have visualization. You instantiate the map object. You look through the layers. You style the layers, and you add the layers to the map. So in this case, we have an example. So essentially, we define the map object. We look through the geometries that we have or we read through earlier in the shapefile. Now we're going to see all of these shape of the lines here, which is overlaid on the map. So we can just overlay through them. So I'm using what we call volume. So volume basically it's a wrapper around the leaflet library. So leaflet is the usual web mapping library that is being used for web applications. So leaflet, so they have it has what we call volume, which abstracts the creation of it. If you're going to do it by hand, it's going to take you a lot of things to do. So when you look at it, you can have all of these components. If you sum it up, you can have as complex as this processing as available. So you can see here, there's a lot of boxes. Essentially, it's doing the same thing. Actually, if you're going to look at it, you're transforming the layer, you're processing the layer, you're gathering the layers, and so on. We're just combining these different layers here, or different boxes, or different processes. Geospatial processing is very simple. It is I don't consider it even as compute intensive. The hard part about geospatial processing is actually gathering the data and making and ensuring that the data that you have gathered is correct. So now some use cases. So we're going to apply the workflow that we've used or that we have defined earlier into the use cases. So we have what we call the site suitability analysis. So this is a project that I've I think 5 years ago. Sorry, 7 years ago already. Wherein you have this. We want to identify the potential resource for ocean renewable energy component. So essentially, we have different layers here, or different data sets. We implement, we did some pre-processing, we combined them, and implement some weights as well. Then from those weights, we implement a suitability map. So if you're going to look at it, it's a very simple workflow. The hard part is actually gathering all of this data because not all of these data are free, and it will take you to do some field work. Will take you, let's say, 6 months to get that data just to pull it in. So that's why when you're dealing with a geospatial scientist, you should not only look at them as a person who just processes or does the office work, but also who gathers the data. Another example or another use case so this is one of my previous projects or research projects before wherein we're implementing land use classification. So land use classification, if it's not known to everyone, is that land use classification implements or these are vital in implementing land use planning and management. So if you're into the real estate and also what you call the building architectures and building those hazard maps and so on, land use classification, planning and management are critical. So this is also similar to it, wherein you have Landsat. So essentially, if just going to look at it, you're just reading through the data and uh, you're implementing those computation. So this is similar to, let's say, Rasterio. Once you implement Rasterio, you implement a NumPy operation or matrix operation to do it. And this is also one of the uh, projects that I did. So this is, if you're going to think about it, this is Waze or Google Maps. You have the traffic. It provides you traffic data or traffic situation. So the idea behind that is that you have, let's say, points, or you can see these small dots here, which are, let's say, your vehicles, and they have what we call the travel time. So this vehicle to reach point 1 to point 2, for example, it will take them 15 seconds. So we tabulated those in a matter of 1 hour. Then we created a surface out of it. So if you're going to think about it, this is similar to how Google Maps works. You just need to get the data. So the data to get all of these, the amount of time to get all of these, it may take you 1 week, 2 weeks, and 3 weeks. But the good thing about, let's say, Google Maps or those situationers, they have historical data, and of course, they constantly get your information while you're using it to go from one place to another. You're sending that data into their servers, and it's being processed behind the scenes. So the algorithm is very much similar in this case. So those are the three cases that I've just mentioned. So just a key takeaway here: spatial data has a lot of uses across different industries, and Python can be used as a tool to leverage this data to build your own application and solve your problem. So, what my goal of this presentation is actually to impart the knowledge of how to process those spatial data. So from here, I just want to say thank you, and the final words here is that from Waldo Tobler is that everything, this is the GIS code by the way, so everything is related to everything else, but near things are more related than distant things. So that's the end of my presentation. So thank you.